we introduce MetaPO, a novel method that aids efficient visual appearance optimization based on a user's preferences. Our method integrates preferential Bayesian optimization with meta-learning to leverage previously constructed preference models from other users to inform the optimization of a visual appearance for a new user. People commonly adjust the visual appearance of photos they have taken. They refine them by modifying brightness levels, contrast, saturation, and other parameters to achieve a certain look for a specific purpose, be it for sharing on social media, creating digital content, or for professional use. However, the parameter space of possible adjustments is large, and it can easily include 10 to 15 variables. This makes manual adjustment time-consuming and inefficient. As a result, most users rely on predefined filters rather than fine-tuning parameters individually, leading to outcomes that allow for little personalization. Prior research has explored using preferential Bayesian optimization to assist users in fine-tuning the appearance. It iteratively asks users to compare a set of candidate images and models, their preferences from the comparisons, gradually refining the images toward an optimal solution. However, this process requires many iterations and is impractical for everyday use. We introduce MetaPO, a novel approach that combines meta-learning with preferential Bayesian optimization for the purpose of efficient virtual appearance optimization. Our method leverages previous optimization experience to accelerate the current optimization, not just for new users, but also for unseen styles and themes. MetaPO follows previous work to present a 2D plane of visual design choices. Users simply pick their preferred option and move to the next iteration. The quality of such search planes determines how quick the optimization converges. If a plane is already well aligned with the user's preference, few iterations are needed, and vice versa. Therefore, MetaPO constructs the 2D plane by incorporating knowledge from past optimizations. Our method defines each 2D plane via 3 key points. Each of them is a specific design in the high-dimensional parameter space. First, the current best design, the user's most preferred design so far, serves as the center of the plane. Second, the most expected improvement option, determined by the acquisition function, which identifies the design most worth exploring. Third, a 2-step forward option, the option that could potentially improve the results the most if the second point were to be evaluated by the user. These 2 latter points are then reflected across the first point, fully defining the plane. Then the candidate images are sampled on the plane and presented to the user. MetaPO includes 2 core elements to leverage previous knowledge in deciding the search plane. First, the population models, built from prior users' optimization data. It captures prior users' preferences and experience, providing knowledge for later optimization processes. Second, the current model, which is unique to each new user. This model evolves dynamically as the user interacts, ensuring personalized optimization. To construct the population models, early users must complete the full optimization process without prior knowledge. As a result, the later 2 points in the search plane are determined purely based on their own inferred preferences. Once the population models are established, MetaPO uses an aggregation-based meta-learning mechanism to accelerate the current optimization process. Instead of treating all past data equally, it assigns different weights to each model based on its similarity to the current user. The more similar a past user's preferences are to the current user, the more influence their model has. For more details, please refer to the paper. We implemented 2 applications, image enhancement and virtual scene lighting design, to evaluate the effectiveness of MetaPO. We conducted user studies with these 2 applications, where participants adjusted an initial image or virtual scene to match a given theme. Our goal was to determine whether MetaPO could transfer optimization experience across users and themes. In the image enhancement task, participants required an average of 9.54 iterations to achieve a satisfactory result, without leveraging prior knowledge. In the cross-user condition, where optimization experience from the same theme was transferred, a new group of participants needed only 5.86 iterations on average. In the cross-theme condition, where prior knowledge from different themes was used, a third group of participants required 7.41 iterations to reach a satisfactory outcome. These results highlight MetaPO's ability to generalize across users and themes, demonstrating its efficiency in real-world applications. For more information, please refer to the paper.